Okay, in this video, we want to find the relative velocities of a boat, a river, and the ground. So to do this, let's start off by drawing a picture. We have a river, which I'll make in blue, and that river is traveling at 2 meters per second due east. So this is the velocity of the river relative to the ground. So it's going to be traveling like this. We're also going to have a boat. Now this boat has a velocity that is going to be 4 meters per second in some direction to be determined. So this is the velocity of the boat relative to the river. What we're interested in is having the velocity of the boat relative to the ground be directly across shore. Now, just as an aside, if you want to find the relative velocity of object A relative to object C, it's always going to be the velocity of object A relative to object B plus the velocity of object B relative to object C. Let's think about this in one direction first. Imagine you were at the airport and you had a giant people mover, sort of like those conveyor belts. So if here is your people mover. And this people mover has a velocity, so if this is velocity people mover relative to ground, and let's say that that is 4 meters per second. That's a pretty fast people mover, but we'll go with it. And then you have a person who has a velocity relative to the people mover of 2 meters per second. So the velocity of the person, well, we pick a different letter. The velocity of the student relative to the people mover is 2 meters per second to the right. That means if we want to get the velocity of the student relative to the velocity of, relative to the ground, that's going to be the velocity of the student relative to the people mover plus the velocity of the people mover relative to the ground. In this case, that's going to be 2 meters per second plus 4 meters per second, giving us a velocity of the student relative to the ground of 6 meters per second. We're going to apply this same concept to this problem, but because this is vector addition, they don't have to be in the same line. They could actually be in any direction. It's just we don't normally think that well in those terms. So back to our problem here. If I label this, this is the velocity of the river relative to the ground. Now, where we want to head is in this direction. We want to head directly across the river from where we started. So we want the velocity of the boat relative to the ground to be directly across shore. What that means is when we add, I'll use red like I did up here, the velocity of the boat relative to the river, it's got to go in this direction. So this is the velocity of the boat relative to the river. Notice the velocity of the boat relative to the ground is still equal to the velocity of the boat relative to the river plus the velocity of the river relative to the ground. It's just that they're vectors. Now, what we're really interested in is this angle right here. In other words, what heading would the boat have to have in order to go directly across? So we're given some speeds. The velocity of the boat relative to the river is 4 meters per second, and the velocity of the river relative to the ground is 2 meters per second. So instead of having the two objects' velocities and trying to find the resultant, they actually give us the magnitude of the resultant. Actually, what they gave us was the direction of the resultant. We still don't know the magnitude. So let's get this angle. If you look at this side, this is kind of like an adjacent side, the river side. So this is like an adjacent side. This is like a hypotenuse side. If I want to get the angle, that theta is going to be the inverse cosine of the velocity of the river relative to the ground, because that's the adjacent side, over the velocity of the boat relative to the river, because that's the hypotenuse. We're plugging in the numbers. 2, it's right here, inverse cosine of 2 divided by 4. So the inverse cosine of 1/2. And that's going to give us a theta that is equal to 60 degrees. So our crab angle here is going to be 60 degrees. The boat is going to have to head 60 degrees north of west in order to keep heading along that heading. Now another related question would be, how fast is the boat traveling relative to the shore? Now we know the heading already is going to be due north, but to get the magnitude, it's simply the Pythagorean theorem. So the velocity of the boat relative to the ground is going to be equal to 4 meters per second squared plus 2 meters per second squared. Take the square root, and that's going to give us a velocity that is equal to the square root of 20, which is 4.47. So this is as challenging a relative velocity question as I'm going to ask. I hope it helps you. You can make up other problems yourself by simply varying the velocities you can solve for the crab angle, or I could give you the angle and ask you to solve for the magnitudes of the velocity. But the concept is the same. When you're trying to figure out the velocity of one object relative to a third object, if you have an intermediate object such as the river, you can solve for that velocity, meaning the velocity of the boat relative to the ground is going to be equal to the velocity of the boat relative to the river plus the velocity of the river relative to the ground. Styles of question I like to ask are boats relative to rivers, and also I like to ask airplanes relative to streams of air. You could come up with a more complicated one with like a people mover that was bigger and had 2 dimensions, but again, the concept is the same. So when you have an intermediate object, the velocity of the first object relative to the third object is equal to the velocity of the first to the second plus the velocity of the second to the third. I hope this helps.